Hello, today I'll be going through using the Forecasting ODE Models Code Toolbox. So the first thing you're going to want to do is navigate over to the GitHub page, which hosts all of the MATLAB code you will need both for this tutorial and applying this toolbox in your own line of work into your own data. Once you've navigated over to the GitHub page, the first thing you're going to want to do is click on this Forecasting ODE Models Code folder. Here you can see the toolbox comes preloaded with many different MATLAB files, some of which we will go over in today's tutorial, some of which are internal functions that allow for the forecasting and fitting using these specified ODE models. And then some correspond to some of the more detailed examples given as part of the full toolbox and tutorial primer. Here you can also see we have a input folder. So taking a look here, within this input folder, we have a couple different data sets, but the one of interest today is the Curve Flu 1918 SF data. So that data set contains information regarding cases that are part of the 1918 influenza pandemic in San Francisco. So once you've taken a look at everything that comes with the toolbox, the next thing you're going to want to do is download the toolbox from the GitHub page. To do that, you want to make sure you're back on this main page. Then you're going to click Code and then Download Zip. So you'll see this zip folder then go to the Downloads folder on your respective operating system. So for me, I can go here to my downloads and then see I have the downloaded zip file here. So you'll want to click on that and then navigate through a few folders to get to this forecasting_ODE models code folder. Once you have that open, you can see all the files that we were just looking at along with that input folder. Next, you'll want to move this Forecasting ODE Models folder to somewhere that will be easily accessible on your computer. For me, that is my desktop, and I've already had this moved over. So I have my Forecasting ODE Models Code folder. Opening that up, you see everything we had before. However, you will want to add an output folder at this point. So I've already added the output folder, and for you to do it, what you would do is create a new folder and then rename it output with lowercase o. So this will be the folder where anything that is exported from the toolbox, so anything related to the parameter estimations, forecast, all of those files will go to this output folder. Once you've created this output folder and have the Forecasting ODE Models Code, like massive folder, somewhere that's easily accessible, you'll then want to take a look at the data structure, which we will do now. So we'll take a look at how your data should be set up. And we'll do this by looking at the San Francisco data. And if you're following along with this tutorial, make sure that the San Francisco data is in this input folder. So we have it here. So that Curve Flu 1918 SF data. And then opening that up, we can take a look. So you can see we have two columns of data here. So this first column corresponds to a time index variable. So this is the idea of we start at time 0, and then we go to time 1, 2, 3, so on and so forth to the end of our data. The second column here corresponds to the incident count data you're working with. So in this case, we're working with incident case data. However, to make this a little bit easier to read, let's flip over to Excel and take a look here. So this is the same data we were just looking at, but in Excel form rather than TXT form. So again, like I said, we have this first column, which is our time index. So it goes from 0 to 62, so through the end of our data. And then we have the second column, which corresponds to our incident cases. So for us, it's cases, but this can be flexible for any type of data. Cases, deaths, hospitalizations, it's really unique to the data that you're working with. To get from Excel to TXT form, what you can do is save as, make sure it's named how you would like, and then save your file as a text or tab delimited .txt file, and then it will be ready to be used as part of the toolbox. Once you've gotten to this point, you're ready to open MATLAB and get started. So let me open up MATLAB. And then once you have gone to MATLAB, the first thing you're going to want to do is navigate to the path where you just saved your new file you downloaded or folder you downloaded. For me, that was my desktop. So I will go to desktop and double click. And now I can see my forecasting ODE models code folder. Before opening that folder up, what you'll want to double check is that this folder is on your MATLAB path. So your MATLAB path is your working directory. So it tells MATLAB where to pull data from, where everything's located. So to double check that, what you can do is click, but make sure it's highlighted blue and not open. And then you can double check that it says remove from path here. So if it says remove from path, it is already on your MATLAB path. However, if it is not on your MATLAB app, so what I just did was removed it so I can show you what it looks like when you need to add it. You'll see this add to path. You'll want to go here and then click selected folders and subfolders because we have some subfolders located within that forecasting folder. So we have our input and output folders. We want to make sure are added into our path as well. So we'll click that. And then next, what we can do is open that folder up. So if you double click on forecasting ODE models code, you'll then be able to see all the files we were looking at before, along with our input folder and our newly created output folder. The other thing you'll want to double check is this file pathway up here. You will just want to make sure it points to the correct folder. So it points to that forecasting ODE models code folder that contains your data and everything we'll need today. So next, what you'll want to do is open the optionsfit.m file. So for us, because we are working with data that comes preloaded, we're going to open up the optionsfit file that is already pre-filled out and corresponds to the flu data we will be working with today. So in this case, we're going to open this optionsfit SCIR flu 1918 dist1_1 file. So when you're naming your options.fit file for yourself, you'll just want to make sure it starts with that optionsfit, and then the following text corresponds to something you'll know what's going on in that file. So here we know this optionsfit file corresponds to the SCIR model, which we will be using throughout our example. I'll go through it in a little bit. We're also working with 1918 flu data. And then that dist1 just says we are working with Poisson distribution, which I'll go through how to specify that in a second as well. However, this options.fit file is a great starting point. This is a file where you will make selections about your data, about the ODE model that you'll be using, and everything you'll need to have ready to go to be able to fit your model. So opening that up, let's start by taking a look at line 21. So this is within the dataset properties section. This is where we'll be making selections about our data. So to start off, what we're going to want to do is provide the data file name we'll be working with. So in this case, we are working with the curve flu 1918 SF data. And if you forget how you spelled your file name, or you couldn't remember exactly what you called your data, what you can do is click on this plus minus symbol to the left of your input folder and see all your different data files you have. So again, we're working with that curve flu 1918 SF. One thing to note here is you want to make sure that this name falls within single quotations. And you do not need the .txt extension with that file name. You just need the file name itself. The next thing you're going to need to specify is in line 23. So this is the CAD disease variable. And this is a string variable indicating the name of the disease related to the time series data. So here we're working with 1918 flu data, so we specify this here. The last thing you need to specify about your data set is the nature of the data itself. So are you working with cases? Are you working with deaths, hospitalizations, or anything that describes the nature of your data? That is what you'll indicate here. So for this example, as we're working with case data, we're going to mark cases here. Once you have made those three specifications, you're ready to move on to the next section. So this is selecting parameter estimation. And the first thing we're going to want to do is select our type of estimation method. So here we have a couple different options to choose from. However, to start off, we are going to be using maximum likelihood estimation, so MLE, with a Poisson distribution, and we indicate that by marking 1 here. However, we could use a nonlinear least squares, where we'd mark 0 here, or a version of a negative binomial estimation method. Next, what we need to define is our type of error structure we want to use in parameter estimation. Similar to estimation methods, we have many different error structures to choose from. However, you'll want to make sure that the option you choose for error structure has or is paired up with the correct estimation method. For example, if you have a normal distribution to model the error structure, so the dist1 here equals 0, you'll want to make sure you have your method 1 set to 0. In this case, since we're working with the MLE Poisson estimation method, we're going to be working with a Poisson error structure here. So our dist1 equals 1. The next thing we're going to want to take a look at is line 63. So this is where we indicate the number of initial guesses for the optimization procedure using the multi-start feature in MATLAB. So we have this set to 10. And then in line 65, this is where we specify the number of bootstrap realizations we want to use to characterize parameter uncertainty. So we have this set to 300. So once you've made all your parameter estimation selections and you have completed the parameter estimation section, you're now ready to move on to specifying some details about your ODE model. So the first two lines here, lines 71 and 72, this is where we specify the name of the model function. And I'll go over in a moment how you can create that model function. But you specify the name of the function you create right here. And you want to make sure that it does start with an @ symbol. So we have @ SEIR1 is we're working with an SEIR model. And then line 72 is where we specify the name of the ODE model we're working with. So we're working with an SEIR model, so we specify that here. Before I dive into the next two sections here, so lines 74 through 89, let's take a look at how we set up that model function to be able to fit and forecast from it. So as specified here, so as we can see here, we're going to be working with the SEIR1 function. So this does come preloaded with the toolbox, and this is just a standard susceptible, exposed, infected, recovered compartmental model commonly used in epidemiology. What we can see here is we are creating a model function f. So here instead of f, we have this SEIR1. So this is the name of our function, and this needs to correspond to the name of the file. So how you save this. And this function returns a column vector of state derivatives. So what we see down here, these dx's, and this is also indicated here. So we're returning these column of state derivatives, and then it takes in inputs of this t corresponds to time, This X corresponds to the model states. This param 0 corresponds to the model parameters. And this extra 0 corresponds to any extra parameters we might want to include. So data streams or static variables are what would be used here. And this extra 0 parameter again is optional. So looking at the code itself, line 9 is where we specify or define the vector of state derivatives we'll be using. So here we're going to be working with 5 different states, and we can see is we have our state variable 1. So this corresponds to the number of susceptible individuals at time t. And here we use our different parameters and state variables to match what the correct ordinary differential equation that corresponds to this S state variable as part of the SCIR model. We specify this here. 2 corresponds to the number of exposed individuals. 3 is the number of infected. 4 is the number of recovered. And then 5 here is an extra state variable that tracks the cumulative number of newly infectious individuals at time t. So we have a couple different parameters here. Parameter 1 corresponds to our beta parameter, parameter 2 to our kappa, parameter 3 to our gamma, and our parameter 4 to our n. And then again, we lay out here what the correct equations are that correspond to each of our state variables. Once you have created this file and specified your ODE function, you are ready to flip back to that options_fit file. So again, here we have the name of our model function we created and the string name of the ODE model we're using. Next, we need to specify the number of model parameters. So again, we're working with 4 model parameters, so we enter 4 here. And then this params.label corresponds to the list of symbols that refer to the model parameters. So these do need to be in the order of how parameters are specified in that function file. So beta corresponds to parameter 1, kappa to parameter 2, gamma to parameter 3, and n to parameter 4. So in line 76, this corresponds to the lower bound values of the parameter estimates. And they do need to be in the order as the parameters are provided. So this 0.01 corresponds to beta, the second 0.01 to kappa, and so on and so forth. Line 77 is the upper bounds of the parameter estimates. And then line 78 is the initial parameter values or guesses for each of the parameters. In line 79, so this params fix, this is a Boolean vector to indicate any parameters that should remain fixed. So should stay at that value we specified in params initial, or should be estimated from the data. So if you want it to be estimated from the data, you would change that to a 0. Or you would change here to a 0. So looking here, we can see our beta is going to be estimated as that's indicated as 0. And then our kappa, gamma, and n will remain fixed at the values we specify in params initial. Next is params.fixIO. This is a Boolean variable indicating if the initial values of the fitting variables is fixed according to the first observation in the time series. Right now we have this set to 1. So that means that our fitting variable will be set to the first observation in the time series. If that was 0, it would be estimated. So next, what we have is this params composite. So this is where we indicate the function that's associated with a composite function of an individual model parameter that we want to estimate from the parameters we specified earlier. If you do not want to include a composite function, you can leave this blank. However, for the purposes of this tutorial, we are going to estimate the R0 value. So let's take a look at that function. So here we can see we have this specified as composite val equals, and then the name of the function. And again, this needs to correspond to the file name. And then our inputs. So we're inputting our parameters. And then line 4 just corresponds to the calculation for R naught using the parameters that we specified earlier. Line 82 is the name of the composite name. So here we are estimating R naught. And finally, line 83 is a variable used to pass, or this is where we would pass any extra parameters that we have. So like any additional data or static variables to the model function. And as you can see here, we're leaving this blank. We don't have anything extra we want to, or any extra parameters that we're working with. Next, we're going to specify some details about our variables. So first, we're working with 5 variables as part of our ODE model. And then in line 86, we specify the labels associated with those. So we have our S, our E, our I, our R, and our C. So this is where we specify which labels go with which state variables. And then in line 87, this is a vector of initial conditions for the model variable. So this is where we specify how we want those parameters to start off with. Line 88 is the index of the model's variable that will be used to fit the observed time series data. So this corresponds to that C, or that state variable keeping track of cumulative infections. And then line 89 is a Boolean variable to indicate if the derivative of the model's fitting variable should be fit to data or not. So if this is a 1, it should be fit. If it's a 0, it should not be fit. Once you've specified these options, you are ready to move on to our final section. So here's where we specify some details about our rolling window analysis. So this is the equivalent of our calibration period. So in line 95, we're saying we want to work with a 17-day moving window size, so a 17-day calibration period. And we want to start this at the first point of our time series. So we want to have our first calibration period start at the first date we have, or first time index we have. And then this T end here specifies what is the start of the last rolling window analysis we want. So here we are just fitting this flu data to the first 17 days of data we have. So we want our start date and our end date to be the same. So we're going to start at the very beginning of our data, and that will be the only calibration period we run. We're only running those first 17 days. And then finally, this print screen option, this is a Boolean variable just to indicate if we want our graphs to print to our screen. Do we want to see our graphs? Now that you have all your specifications made within your options_fit file, the next thing you're going to want to do is run the plot ODE model function. So before fitting the model to data, it is helpful to check that we have correctly specified the model by checking that the model solutions for the parameter ranges specified within the options.m file correspond to a broad range of expected solutions. So we can do this via the plot ODE model function. And what we're going to look for is any unexpected patterns that are not in line with the theory behind our model, which will then suggest the presence of errors maybe in how we specified it. And those are errors that do need to be fixed before we continue on with our analysis. Moreover, so comparing the range of model solutions with the data that we intend to use for estimating parameters in the next step is useful, because we can also get a good idea if the way we specified our model can result in a good fit to the data, or if we need to make some adjustments to the parameter ranges before we can proceed to fit the model to data. So to run the plot ODE model function, what we can do is type plot in our command window, type plot ODE model in parentheses at. And then what we're going to want to use is the options fit SEI our flu 1918 dist1 __1. So the name of our file. And we can also copy and paste that from right here as well. So once we have that specified, you can hit enter and give this a go and run it. For the purposes of time, I have pre-run this, so let's take a look at the output. So looking here, we can see the plots of model solutions for the SEIR model we specified earlier with the parameter ranges and initial conditions we provided in the options.m file. So starting first, this black dashed line here is a median of the sample model solutions, and then the red circles correspond to the time series data. So the second plot here is the one we really want to take a look at. This zooms in on the region of the left subplot in the range of the data. So we can see how well the model trajectories follow closely to the data. And here it does. So that's kind of indicating we might have a good model fit. Once we have checked this, next thing we can go ahead and do is fit our model. So what we're going to do is run the run fit ODE model code. So how we can do that is similar to the plot ODE model code. So let me delete that so it doesn't run. What we would do is type run fit ODE model. And then we will want to use the @ and then the name of our function again. And then this, or when running the run fit ODE model, we have a couple different things we need to add into when we're calling that function. So we also need to indicate that we have a t start of 1. So that is similar to what we indicated down here, that our time point for the start of the rolling window analysis is 1. Our t end is 1, meaning that we're only running that one calibration period, which starts at the first time index or start of our data. And then we want to run a 17-day long window size. So we put that as 17. This takes a little bit to run, so I'm not going to run this right now. But from here, we get quite a few different outputs. So taking a look first at the figures that we get, we can see how well our model fits to the data. So this is one of the graphs we will get with fitting the SEIR model with Poisson error structure to the influenza data. We can see our different parameter estimations up here. So we have our beta, our kappa, our gamma, and then our n. And then we can also visualize the model fits down here. So what we can see here is there's decent model fit. So in terms of the graph itself, the red line here corresponds to the median model fit. The gray lines correspond to the model fits obtained from the 300 bootstrap realizations we specified earlier. The cyan lines indicate the predictive uncertainty around the model fit, so those bluish looking lines. And those dashed lines that we can see on the top and bottom correspond to our 95% prediction intervals with Poisson errors. Once we have run this, the next thing we can do is run the plot fit ODE models function. So you cannot run the plot fit ODE model function until you run the run fit function. So to run the plot fit, we do the exact same thing. So instead of having this run here, we can change this to plot. And then we want fit. So we want plot fit ODE model. And then we want the name of our options file, our t start, our t end, and then our calibration period sets. So again, I am not going to run this right now just for the sake of time. But from this, we would get 3 CSV files to our output folder that we created. So going over to our output folder, you can see we have quite a few different Excel files here. So the ones we want to focus on are the fit model. So the fit model name, SEIR, the parameters rolling window analysis, and then our performance calibration. So these are the three that you will get anytime that you fit a model. And what these look like, so the fit model, let this open up. So this includes our time series data, and then the median model fit, and our lower and upper 95% prediction intervals. Our parameters rolling window analysis looks like, I'll let this load for a moment. This includes our parameter estimates along with their upper and lower 95% confidence intervals. So we have our beta, our kappa, gamma, and n. And our performance calibration includes the calibration performance of our model fit. So I'll let this open up. And here you can see our overall 95% PI coverage isn't great. So that kind of indicates we might want to fit with a different error structure, which we'll do in a moment. The other file that we get with this is the parameters composite model name. So this is because we indicated that we wanted a composite variable or that are not. And we also get our upper and lower confidence interval estimates along with our mean composite measure. In terms of graphical output, we get a figure that looks like this. So we can see our model fit down here. And we also can see our parameter estimates along with their 95% confidence intervals up here. This indicates that we might want to try fitting a different error structure. So here what we can do is repeat the process we just went through, however, using a negative binomial error structure. So let's take a look. What we would do to indicate that is here, instead of having, before we had model 1 or method 1 and dist 1, we would change that to 3 and 3. So what we can do then is we would run everything the same. I ran all of this for us already to save time with this tutorial. All the outputs would look similar to the Poisson, but what we did find with the negative binomial error structure was that coverage was a lot higher with that compared to the Poisson. So let's take a look at that graph. So again, we can see our coverage down here, and a lot more of those points from our time series falls within the upper and lower bounds. With all of this output as well, we get the empirical distribution of our composite parameters. So again, our basic reproduction number here. This is corresponding to when we fit with the Poisson error structure. And we can see this is what is obtained by fitting the SER model to those initial 17 days of the data. So you are now ready to start getting things together to be able to produce forecasts from your model. So the first thing you're going to want to do if you're following along with this tutorial is open the options forecast SCIR flu 1918 dist1_3 file. So opening this up, you can see it looks very similar to the options file we were looking at before. However, a few changes to know. We are going to be working with, so for producing forecasts for this example, we're going to be using the negative binomial estimation method and distribution for error structure. This is based off of the model fits we were just looking at. So with the model fit being a little bit better for that negative binomial, that's what we'll be using here in producing and our forecast. The other new thing here is this forecasting parameters section. So here you can see we have two things we need to select. So first, we want to get our forecasting performance. If you do want your forecasting performance metrics, you indicate a 1 here. If you do not, you indicate a 0. And then We also have to indicate our forecasting period. So this is our forecasting horizons, or the number of time units ahead we want to forecast. So if you're working with weekly data, this 10 here would correspond to 10 weeks ahead. If you're working with daily data, like we are now, this 10 corresponds to 10 days ahead. Once you have everything specified within your options forecast file, what you then want to do is run the run forecasting ODE model file. So to do that, what you'll do is go down to your command window, type run_forecasting, an ODE model, and then a parentheses, and then you'll do @ and then the name of your options forecast file. So options forecast SCIR flu 1918 _dist1_3. Similar to the running the run fit, you'll want to specify your T start, so 1, your T end, which is 1. You want to specify you want a 17-day moving window size. And then finally, one new input here is your forecasting period length. So we have a 10 here. Once you have all the inputs entered, what you would do is hit enter and your model would be fit. And then you would also get some information about your forecast. However, for the sake of time, I am not going to run this, and we will take a look at the output from this function in a moment. However, once you run the run forecasting ODE model function, the next thing you're going to want to do is run the plot forecast ODE model. So the plot forecast ODE model takes the same inputs as the run forecasting ODE model function. However, you will want to change the function. So here we want plot forecast ODE model, and then everything else is the same here. We can take a look and see our different outputs. And these are the exact same plus this forecast model that we would get with the run forecast function by itself. So here we get our AICs for the model. And we also get this when we run the plot or the plot fit and the run fit. We get our forecast. So let's take a look at that. And here we can see we have a column that corresponds to our time index, our observed data, our median predicted or median model fit, along with our median forecasted values, and then our upper and lower 95% intervals. We get the parameters of both the rolling window analysis and composite, as we did with the options.fit and the run fit. We get the performance metrics for a calibration model. And then we also get the performance metrics for our forecast, which look very similar to our calibration forecast metrics, where we get our MAEs, our mean absolute error, mean squared error, 95% coverage, and our weighted interval score. And then here we can see this is corresponding to a forecasting horizon of 10. In terms of graphical output, we get quite a few, but some things to note here is looking at this graph first. What we can see, it's very similar to the graph we get with the options fit, run fit, and plot fit functions, where we have our parameter estimates and their 95% confidence intervals at the top here. However, this graph below looks a little bit different than what we got before. So what we can see here is a couple different elements. So starting first at this red line. So the solid red line is the median model fit. These blue dots here correspond to our observed data. Our cyan lines indicate the predictive uncertainty around the model fit. So these light blue lines. These gray lines, which I know are kind of hard to see, so let me zoom in. So these gray lines we see here around the red correspond to the mean model fits obtained from the parametric bootstrapping with 300 bootstrap realizations. And then these dashed red lines correspond to our 95% prediction intervals. And finally, this vertical dashed line, this separates the calibration period, so on the left, and the forecast on the right. Then let me zoom back out. So looking here, we can see coverage is okay, which we saw with our performance metrics for the forecast. So we saw have about 70% coverage, and then we also have our MAE, MSC, and WIS metrics here. And then with that as well, we also get a graph showing these metrics over our forecasting horizon. So ultimately, we can run this toolbox with many different types of models. So as part of this example, I'm not going to walk through all the steps, but we can also run it with things like a exponential growth model. Here we can see the exponential growth model, calibrating the model with the first 17 days of data, like we did with the negative binomial and the Poisson models. Again, the solid red line corresponds to the median model fit, and everything else is the exact same as before. But instead of using an SCIR model, we use a exponential growth model. So what this shows is this toolbox has a lot of flexibility in the types of models that can be fit, and is a great resource for fitting models based off of ordinary differential equations.